multivariable functions. That's what we're dealing with. This section is the start of Calc 4. So when you do Calculus 4, you'll begin, actually, if you do Calc 4, it's pretty much all about multivariate functions. How to differentiate them, how to integrate them, all sorts of cool stuff like that. But we're going to deal with multivariable functions, and I keep talking and people keep joining. So let me, oops, didn't mean that. Let's get them in, and then we can continue. Nicholas, last one, definite. Okay, put that over here. So what is a multivariable function? Well, let's do 141. That is a function from Math 141. It's actually two-dimensional. And what do I mean by that? Well, if you draw it, it looks something like that, right? And it is basically it's a curve in 2 dimensions. But it only has one variable, right? X. And for every X, there is a corresponding Y value. And it's not uncommon for us to write down functions using Y equals, right? Both notations are equivalent. Well, a multivariate function, this is one example of them, is that. Now in this world, X and Y are both variables, and for any given X and Y, you combine them and you get this fella. And this is very often also written down like that. And if you try and sketch that, you don't get a curve or a line in 2D space. And it shouldn't surprise you, isn't that a 3D thing? Now, if you try and sketch it, it looks something like that, right? Kind of draw little curvy lines, trying. Not the easiest thing to draw in 2D paper, not the easiest thing, but we have software that allows us to do it, and we'll be actually using quite a lot of software today. And so very visual today. Some of the questions you're going to get is, here is this function. There are 4 pictures, which one is it? And you can take this guy and then you can use the software and basically just match it. It's as simple as that. But that's still to come. So theoretically, couldn't I do another function? And I don't know, I might call it W. Now, if I try to sketch what that looks like, wouldn't that be a 4th dimensional thing? Which means, again, you're not going to draw anything 4th dimensional, right? So we can visualize up to these. And then after that, trying to even create pictures of it is a redundant process, right? It's not going to work. It just isn't. And that's fine. We like to visualize things, but sometimes you can't, right? I can't draw a picture in 4D, and there isn't any software that I know of that can do it either. Doesn't mean that the function doesn't exist. It does. It's a multivariate function. This is a 3-dimensional. This is a 3-variable function. This is a 2-variable function, and this is a 1-variable function, right? So multi means more than one. So we're only going to focus on 2 or more. So these are the main things that section 14.1 is going to deal with. The first one is evaluating a function, and that is very, very simple. It is essentially plug and chug. So if somebody says find f of 10,3, that's the x, that's the y. So the answer is 10 squared plus 3 squared, and your answer is 109. Would you agree you're not going to have many problems evaluating a function? Right, if you tell me who it is and you want me to evaluate it at this given point, it would be that. So if you can imagine my little picture here, and I'm just cheating with the scales, can you imagine that's 10, 1. That dot there would have a height of 109. So you plug in an X and Y, and then the height of it is Z. Can you tell that at the origin, this will have a height of 0, for example? Now, what's the next thing? Well, let's look at domain and range of a function. Now, in Calc 1, isn't the domain in English usable values of X? In other words, the domain is what are the values of X you can use this formula with, right? And sometimes it's all real numbers, but other times it might be X has to be greater than or equal to 0. Can you imagine if I did this function, for instance? Wouldn't the domain be X has to be greater than or equal to -1? If I did this function, wouldn't the domain be everything but you can't use 0? So what's the domain? Let's focus on that first time. What's the domain going to look like? Well, we have to kind of expand how we write down domains. So I'm using this guy again. It's now, it's usable values of X, Y. So for what pairs of X and Y can you use this function? Now, would you agree for this function here, you could use any X in the universe and any Y in the universe? So how would we write that down? Well, we have nice ways to write it down. Keep referring back to this guy. See, in this case here, couldn't I just say that the domain was all real numbers? Couldn't I write it like that? Which is a nice short way of saying it. Now, I could have written it down in interval notation, which is a bit clunky, but it would work, right? I could write it down in set builder notation, but I think set builder notation would be quite messy with that particular example. Now, in this case here, back to this one, how do we tell people what the domain is? Well, since you can use any value of X you like and any value of Y, there are a number of notations that can be used. Here's one notation. The first bracket is the interval of X's. I know it looks like a cross product, but it's that you use symbols for different things. It basically means in the next dimension, right? So in the X dimension, you can use these, and in the Y dimension, use them. You could call it R cross R. You could call it R squared. If you're economic, would you agree that R squared is just the simplest way to tell people you can use any X and any Y that you like? So let's look at a function whose domain is not everybody. How about this function? Right, for this particular function here, can you use any X you like, from minus to plus infinity? Agreed. What about Y? Can you use any Y value and still get a real answer? Because we're talking real numbers here.
It has to be positive.
Has to be positive. So if you were trying to break this down and you wanted to describe the domain, here are a number of ways you could do it. Couldn't we just say negative infinity to infinity for the X's and square bracket, because you're allowed to use 0, infinity for the Y's? Would you agree that that is basically the domain, right? It's a concise way of saying it. You could say R cross that. Would you agree that's maybe a little bit shorter? Now, in set builder notation, you might write it like that. You see that funny E symbol? It means X belongs to the real numbers. So there is a number of different ways in which you can write down a domain. I've got a few people coming in here. Excuse the hesitant. I'm trying to find some. Ah, here we go. Gotcha. Right. Now, let's suppose we have a function. Again, we're interested in its domain. And its domain is going to be that. Now, when the domain is relatively straightforward, you have quite a few different ways to do it. When it's messy, for want of a better word, right? The X and Y's are all intertwined with each other, right? They're interacting with each other. You can't really do it like these two. It doesn't work that way. So you fall back on set builder notation. And you basically, they all look like that. And where the dots go, you just put in what needs to be true. And so this would be how you would write the domain for this function. So basically, this is your template, and the dot, dot, dot is whatever the restriction is to make your function work. How about this one? Let's use G so I'm not too caught up. Okay. That function there can be used except when.
Either X or Y or 0.
Or if you put that together, X, Y can't be 0, right? Because you could have X2 and Y42, that's okay, but X2 and Y0 is not okay. So you just say X, Y are equal to 0. Does that make sense how you would describe usable values of X, Y for the more complicated questions in terms of the restriction, right? What needs to be true for it to work? Here's an example of a domain function, a domain question. Any problems with the X's and Y's in this question? Can there be any?
Is that a
Sorry?
7Y or a 2Y? What is that?
It's a 2, very badly drawn 2. Even if it was a 7, wouldn't the answer be there's no problem? Right. Now, if you're no problems with the X's and Y's, can't you just tell me the answer, or describe the answer, whatever you want to do it in terms of just that? Now, this is not a homework question directly, but it could happen. Is there any problem with this function?
The cosine cannot be 0 equals
Right.
0.
So why don't you just do that and then just stick, my little template around it? You see how you would describe the domain by the restriction, right? What's not allowed to harm or what is allowed to harm? Because sometimes you phrase it in terms of the thing inside the square root must be greater than or equal to 0. Are we comfortable with domain then, right? You don't get too many questions, but a multi-variable function has a domain. So let's return back to this one. And let's now look at the range. If you did, where's my little picture again? Because it's kind of helpful to do a 2D one. If I was asking you, what is the range of this function, right? X squared plus 1, wouldn't you basically say it's the range of y values? So what does the y's do? Well, in this case, the range would be y is 1 or bigger, right? That's the range of your answers. So when you do this question, I want you to think of what is the range, if I call this z? What are the range of values that z would take in this situation? And I'm going to do it by set builder notation. Right, x squared plus y squared. What's the range of values that z can take? Well, let's start with the smallest. What's the smallest answer that x squared plus y squared is going to get you? I hear 0. Right. Finn's mouth was moving, but I saw the word 0 going out there, right? Isn't there no limit to how big it could be? So the range would be 0 to infinity. How about this function? Now, I know 5x plus 2y could be any number in the universe, right? It could be minus a million, a trillion, plus a billion, a zillion, right? All that good stuff. But the cosine of it, which is the entire function, what's the range?
-1 to 1.
Agreed. Because a cosine is still a cosine. And isn't the biggest number a cosine can be a 1? And the smallest the cosine can be is -1. Agreed? Now, how about this function? What's this range?
-infinity to infinity.
Which we could also call R. Now notice it's just a single R, right? A domain is a two-dimensional thing, right? But isn't a range a single number, a scalar thing, right? So domain and range are different even in the way that they're written. In multivariate functions, domains are 2 or 3 or whatever dimensions, 2 typically, right? The x's are here, the y's are here, but in a range isn't a single answer, right? A single dimension, or single interval. Any questions about domains and range, or do you feel comfortable about how you go looking at them and what you do?
So I'm a little confused why in our first example of x squared plus y squared, the range was from 0 to infinity, but our last one, the range from x squared minus y squared is all real numbers.
Okay, so let's show you the difference here. Do you know how these two guys are being squared first? Now, when you square something, don't you make it positive? So the smallest you're ever going to get here is 0 squared plus 0 squared, which is 0. Now, how big can this be? This can be as big as you like. Don't you just make x really big or y really big or make both of them really big? Would you agree that infinite is the biggest answer. So if you're looking at what could that be equal to, the smallest that I could ever equal is 0, and the biggest it could ever equal is as big as you like, infinity. Now this one, because you're subtracting, couldn't you take a really small x and a really, really big y? And if you calculated it, couldn't the answer be really big and negative? In fact, negative infinity, if you think about it. Couldn't you make it as negative as you like by making this x huge?
Mm-hmm.
And if you switch places, couldn't you have a positive answer by making x extremely large and y tiny?
Yeah, okay.
And so these are different because the restrictions on the calculation tell me that what you get in one situation is not quite the same as in another.
Right.
Just for one last example. E to the power of 1 over xy. What's the smallest answer you can ever get for e to the power of 1 over something?
1.
Because e to the 0 is 1. If you choose really small x's and really small y's, won't 1 over a really small number be a really big number? And e to the power of a really big number gets me infinity. Does that argument work? You know, if I pick x as 0.001 and y as 0.0001, this will be e to the 1 over 0.10 zeros, which is the same thing as e to the power of a billion. Huge. Now, there's one little hiccup. Curved or square? I know the smallest answer you can ever get is 1, right?
Because the
But
fraction, wouldn't it be curved?
Yes,
We can't
because
have 0 in the denominator.
you can't get 0 in the denominator. So the closest you get is almost 1, right? So there'd be a little tweak there. Maybe I should have kept away from that one because that's probably harder than anything you're going to see.
I have a quick question.
Yes.
So about that same problem,
Mm-hmm.
I am curious about why it can't be less.
What, less than 1?
Because if you have the exponent make
Oh,
it
let
negative.
me sketch what e to the x looks like. Oh, you could have negative x's. Okay. There, fix the problem. Right. So in this case, you're going to have e to the somebody. I was going to say if you do e to the somebody, they typically look like that, right? And this fella along here is 1. No, it isn't. It's 0. Because you get really big numbers. That's just to make it positive. So that's why I did that. Because you get big numbers, e to the 1 over a billion. E to the 1 over a billion is still going to be e to the 0 is 1. And if you go small, e to a very small thing, no, it's still going to be 1. Yeah, it's still 1, both cases. Right. My little checklist. Done, done. Now, how do you draw these darn things? And after that, hopefully we'll have time, contour maps. Well, what you do is you let software do it for you. If I went and said to you, draw x squared plus y squared, right? The one I draw in my little picture. I guess you could probably do it because you've seen it enough times, right? But the minute you make the function really complicated, you're not going to be able to draw it by hand, right? I don't think that is that's something I would expect you'd be able to do. I'm having window issues. Here we go. Basic. And I have, if I can find it. God, I need new eyes. Is it this one? Nope. Got it. Okay. I have GeoBra, which, darn it, I've made it and it went away. There it is. Are you looking at GeoBra right now? Yay. Okay, so you're going to get a bunch of questions that says, here is a function, what does it look like? And they give you 4 pictures. Do you know the kind of A, B, C, D thing? Right, so you'll go up here and you'll type it, and then you'll see it. And it's been a while since we did GeoBra, but isn't it kind of cool that you can rotate it and have a good look at it? So if you got a question like, taking my life into my own hands here, sine. Oh, sine. Didn't do that before. 5x plus 2y. Hey, okay. It looks like, I know, like corrugated paper, right? Probably the scale's not great. So how about if I zoom in a little bit? There. Okay, it helps a little bit. If you orientate it, this blue vertical line is the z-axis, right? Can you see why it goes from -1 to +1? Can you see? You know, trust me, it does, right? Now, when you look at this, can you also tell that the picture, you can keep going in any direction and it works forever, right? So how much zoom in can I do? Well, that's probably actually quite a good zoom now. There. Do you get a better feel for the shape of it when you zoom right in? And you can see your function. And that's pretty much it. So can you imagine you're going to get a question, here's the guy, 4 pictures, who is it? You may have to zoom in a bit because I don't know, you know, what their pictures look like, right? So you may have to zoom in a little bit just to see them clearer. I'm going to try that one that we had issues with. Now, what was it? It was, can I do e to the power? Yeah, you have to hit that button to get e. And then I can do the power. Oh, why not? To the power of. It was a fraction, wasn't it? Where's my fractions? Can I get fractions here? I should be able to do it as 1 over xy. There we go. Boop. What an interesting function. Oh, that's very interesting. Oops, I killed it. I killed it. I didn't tell you the right domain. The 0 and 1 are the domain. I know how to kill it. I don't know what to do. I've killed it. Oh, darn it. Right, go back out and then again, I guess is the best you can do. So if I kill this one, just delete it. There we go. I'll just put something boring in. If I haven't totally broken it,
I think you need to
Try
zoom
hitting
in.
the home button.
I need to do what?
I think you've zoomed out too far. Is there a
That's not-
zoom to fit?
No, I'm just trying to make this function go away. That was my goal. I just wanted to replace it by a different function. Me and software are having issues there. That was the function I wanted. There we go. So so if I hit this button, maybe I'll get it back. No. Anybody get any ideas how to get this back?
Try hitting the little house icon
Where is it?
above the zoom. The little magnifying glass at the bottom right.
Bottom right.
Oh, see it. Go back home. Oh, look. It's went tiny.
Should have reload the page.
I gotta wait around this. Copy. Close it. There we go. And this was the second one, third time lucky. Oh, there's what x squared looks like. It's kind of interesting. Can you see the y equals x squared shape, and then you generate it along one of the axes? And then I'll do plus y squared. And boom, yeah, your little guy. Now, if I take this guy and add an xy, basically just ovaled it out a little bit. So how about if I just add, hopefully it'll take a sign. Yes, it did. Anything particularly interesting? I'm frightened to break it. No, nothing too interesting. How about stick a 10 in it, then make that term a little bit more violent? That might help it. Ah, it did some damage now. That's an interesting shape. You see what adding 10 sine x has changed my surface quite in a quite a major kind of way. If I shrink back eventually, it generated a little baby. You see the little baby to the right? And then, oh, that is a cool shape by sheer randomness. Look, is that not cool? Yeah, okay. I've wasted enough time. You can have hours of fun drawing, with one exception where I broke it, functions. And so I should show you what your homework looks like so that you get an idea of what you're being asked to do. So let me shrink this back a little bit. Are you all looking at chapter 14.1 homework? Okay. I've got these windows. I'll move over here out of the way. Here's a function. Sketch the graph. So you see there's 4 pictures and one of them is that guy. And make sure that you know which one is the right orientation, right? Is it this one or is it that one? Here's a new function, pick the graph. Can you imagine how quick your homework's going to be? At least for these questions. Here's your function, pick the guy. Just curious, does anybody know what the answer to question 4 is? Which one of those 4 shapes would you get from that function?
Is it the sphere?
It is. What made you think that? Well, let me rephrase that. I've thought about it a bit more and it's not a sphere anymore. But it would have been a sphere if it had been x squared minus y squared, but it's 4x squared minus y squared.
The bottom right.
Yeah. Now, I didn't pay enough attention to it. Do you see that 4 that's here? If that was missing, you would have got the sphere because the x squared and y squared would be balanced. But because you're doing 4 x's and y, do you see you distort the sphere in a kind of elliptical way? But you plug it in. There's 6 functions and 6 guys. So you plug it in, and I'm making this up, and you think it's the second picture. and that's what your answer looks like. And we're now going to start the last thing. Would you be happy about that you can use software to draw the pictures, and which one of the 4 or 6, whatever they give you, you're done, right? That's pretty much all you'd be expected to do. So now we're going to look at contour maps. I'm going to pick a guy that I can draw relatively easy and show you what contour maps can be used to do. Right. That is very, very roughly what that guy looks like, right? If you did it on GeoBra. Now, have you ever done, and some of you I know are I'm not very good at drawing things. There. Have you ever got contour maps, right? Paper, physical, old-fashioned maps that try and describe what 3D terrain looks like. They're called contour maps. Right. So if you were looking at a place and it looked something like this, wouldn't that be 2 hills that are probably the same height, right? On the other hand, if it looked like this, wouldn't this be a little hill with a big hill next to it? So can you imagine that you can use these to visualize 3D things? And that's what they were used for in maps. Noah, since you're the hiker, climber kind of guy, do you ever use contour maps when you go out hiking and doing stuff?
I've used them. There's a few apps that make it a bit easier to kind of get an idea of how the trail changes, but I do try to look at the terrain before I go.
Right. So these are basically ways to try and visualize a 3D terrain in a 2D format, because even in your phone, it's kind of 2D still, right? It's a flat screen. What kind of puts contour maps is that all the lines, all the points on these lines are the same height. So this could be, you know, the 10 feet level, the 20 feet level, the 30 feet level, right? So 10, 20, 30, 40, 50, you know, all the way up. So can you imagine taking this shape, the one I've got, and you slice it at, say, the 2 meter mark, and then you slice it at the 4 meter mark, and you slice it at the 6 meter mark, you will make a contour map. And it might look something like this. And can we pretend that each line goes up in increments of 2? This would be the contour map of this shape. Now, do you notice that they're made out of circles? Well, think about that. If you take this shape and you slice it, won't it be a circle? Now, as you slice it at the 2 feet mark, the 4 feet mark, the 6, the 8, and the 10, do you notice that the gaps between the circles, I know I've drawn them really badly, but can you imagine that the gaps are quite big at the start and then they get closer at the end? Because at the 6 feet cut and the 8 feet cut, won't there be very little difference, right? Going 6 to 8 is quite steep. So when you see contour maps and the lines are close together, doesn't that mean it's a steep part of the mountain or the hill, right? And if the contour lines are quite far apart, isn't that just a very gentle hill, right? A very gentle climb up or downhill. So how close the lines are is a reflection of steepness. So these are called contour maps. I'm only going to draw one of these by hand to show you how you would do it, and then we'll show you that software does it for us. So I'm going to try and create a contour map for this guy. So what you do is you set up a set of equations. Have you noticed that I've made it 0, 2, 4, and 6? That reflects the slice at the 2 feet mark, the slice at, see, I'm saying Z is 4 here, right? Can you think of that as being Z, the height? Now, what does that look like? Well, it doesn't look like very much. Doesn't it actually look like a dot? It's the origin. Now, what will this look like? Well, won't this look like a circle radius 2? So, okay, imagine, not 2, sorry, a circle square root of 2. So that'd be about here. Okay, don't laugh if it doesn't look like a circle. Can you pretend it is a circle, right? That would be this one, square root of 2. Now, wouldn't the next one be a circle radius 2? Wouldn't the next one be a circle radius square root of 6? Which I'm not going to make any great attempt to do. Can you see I'm now creating the contour map for this surface? So that's how you create a contour map by hand. But we want to do it using technology. What's the chances I screw this one up and break it at least once? Right? Don't take bets on it, you'll lose money. So here we go. Both this new piece of software, the contour map one, which of course I can't find. Where are you hiding? You here? Here we go. Okay. Are you now looking at something that's called Contour Plotter? Right. It's in your Canvas site, so you click on it and it's called Contour something. Right. You put your function over here. So in my case, it's what going to be x squared plus y squared. And hopefully I don't need to change any of these. I'll update it. There you go. Can you see concentric circles? Kind of cool. Do you notice at the beginning the gaps are quite big and then they get closer and closer and closer? Isn't that reflecting the steepness as the shape travels away from the origin? Now, if you put a negative in here, I'm likely to break it, but I feel brave, so I'm going for it. Whoa, I didn't break it. Now, what the heck does that shape look like? Well, there's its contour map. And if I do this little slider, there, not a lot of lines, right? Because sometimes too much is too much. There's a few more, but there. So when you slice this shape horizontally, right? Slice it parallel to the floor, you get all the points whose height is 1, all the points whose, you know, the curves at heights of 2, heights of 3, heights of 4, and you would get this shape. That is x squared minus y squared. And I'm going to go here. Are you still, I hope you're still seeing GeoBra. Do I have to go out and in? Okay, so when I do this fella, And I want to go in or out? In probably. Can you see that X shape that you were noticing? And when you look at this surface, can you see this surface has a funny little saddle point that's called right here? Quite a weird shape, isn't it? But we have contour plot. And okay, let's try and break it. Will you all say hi as I try and break this thing? I did break it. I wonder if you need to do a capital sign, maybe. Maybe put a space in it. Will that help? Okay, you can't get X, Y's. Okay, I'll break it a different way.
You probably didn't like the space in the sign.
Yeah, I tried it with and without. Oh, it's just been awkward. Oh, some interesting things. Okay. I think I did manage to break it, but you can play about with it. And contour maps are kind of fun. Hopefully this one can take signs. I'd be really disappointed if it couldn't take at least a sign. Okay, it can take a sign. Why can't it take a sign of X, Y? Well, maybe it is taking a sign of X, Y, you just can't see it. Oh, that's possible. What about an X plus Y? Would that help? Oh, that is the contour plot. It's working. It's not what I thought it would be. But can you imagine a sequence of hills at an angle? When you slice it, don't you just a whole load of parallel lines? Cool. It does do the sign of that. Oh, I'm happy. Right. That is us for today. We learnt some